This is Euclid Book 10, proposition number 17, and I need to pause for just a moment to define a particular term, and that term is parallelogram. What is a parallelogram? Okay. A parallelogram is a four-sided figure. As you can see here, all four of these are four-sided figures. This is a square, this is a rectangle, this is a rhombus, and this is a rhomboid. Okay? Now what makes all four of these parallelograms is that these two sides are parallel and these two sides are parallel. This is parallel to this, this is parallel to this. Same thing here. These two sides are parallel, these two sides are parallel. Same thing with this and same thing with that. Those are parallelograms. Okay? So you can't just say, well, a rectangle is a parallelogram. Well, it is. But a rectangle is not the only parallelogram. A square is a parallelogram, so is a rhombus and a rhomboid. They are all parallelograms. This is very important for this Euclid proof. And I will show you that in just a moment when I draw you the illustration for Euclid Book 10, proposition number 17. Sounds real simple, right? Yeah, you have no idea. In Euclid Book 10, proposition number 17, you have two lines. You have line A, and then you have another slightly longer line, and it's B, C. Now this line is divided up into several different parts. Ta-da! All right. Now then, whenever I say rectangle, I mean, okay, and I'll have to define this for you. I've already defined a parallelogram. A rectangle is a parallelogram, but rectangles are not the only parallelograms, as you've just found out. This is a rectangle, and this is a square. So anytime I say the word square, I want you to visualize this. Anytime I say the word rectangle, I want you to visualize this. And when we're going to be talking about squares and rectangles, we're going to be talking about square areas and rectangle areas. Okay? We're not going to be talking about a square and a rectangle. We're going to talk about all the space inside the square and the rectangle. This is very important for this particular Euclid proof, and I'm going to show you that right here. Now this is the rest of the illustration. You can go ahead and take a look at that. Okay. Now we're going to take this very slowly because there's a lot of detail to this one. As if you didn't know. If there be two unequal straight lines, well, A obviously is not as long as BC. We know that now. And to the greater there be applied a parallelogram. Remember, that could be a rhombus, that could be a rhomboid, that could be a rectangle, it could be a square. As long as it's a parallelogram, it doesn't matter which one it is. Okay? Let's go on to this. And to the greater there be applied a parallelogram equal to the fourth part of the square on the less, and deficient by a square figure, and if it divide it into parts which are commensurable in length, then the square on the greater will be greater than the square on the less by the square on a straight line commensurable with the greater. Are you confused? I bet you are. And if the square on the greater be greater than the square on the less by the square on a straight line commensurable with the greater, and if there be applied to the greater a parallelogram equal to the fourth part of the square on the less, and deficient by a square figure, it will divide it into parts which are commensurable in length. Now you're probably spinning at this point. Okay. Let A and B and C be two unequal straight lines, of which BC is the greater. I've already established that. And let there be applied to BC a parallelogram equal to the fourth part of the square on the less. Wow, what does that mean? All right. So what that means, we have a parallelogram, one of the sides being BC. Now I'm going to draw it like a rectangle because a rectangle is one of four parallelograms. You know that now. And it's going to be equal to 1/4 of the square on A. That's the equation, folks. I'll bring it right up to you so you can see it. That's the equation. Now, what does that mean? It means, as I said way back in book 1 and book 2 and so on and so forth, you know this if you studied all my Euclid Elements videos. You should know this by now. It means that if you draw a square and all four sides of the square, the length of all four sides is equal to the length of A, that's what it means. Okay? Now it goes on here. And let there be applied to BC a parallelogram equal to the fourth part of the square on the less A, which we already showed you, that is equal to the square on the half of A. Okay. So now, what we're going to have oops, hold on. So basically what we're going to have is first, and I could actually put this like this. I really should. Or we could, I could actually, let me do it this way because it'll be a lot more clerical if I do this. Hang on. So basically what they're saying here is you're going to take A, okay? You're going to take A, you're going to divide it by 2, and then you're going to square it. Okay? That's what he's saying. You're going to take A, you're going to divide it by 2, then you're going to square it. Alright? And deficient by a square figure. Now the square figure, we'll show you that in a little bit. Let this be the rectangle BD and DC. Now this is from the lemma that we had in the last Euclid proof. If you go back to Euclid book 10, proposition number 16, you're going to see a lemma right over there that will explain this, okay? So now we have a rectangle BD and DC. So what that means is that you're going to have a rectangle. Two of its sides are going to be the exact same length as BD, and two of these sides will be the exact length of DC. That's what that means. Okay, I'm going to show this to you so you can see that. Okay. So is this starting to make sense to you now? Okay. Now, BD is going to be commensurable with DC. That means that there's some number out there that can measure both BD and DC. Now Euclid says, I say that the square on BC is greater than the square on A. So, if you were to draw a great big square on BC, in other words, you had 4 sides and each one of those sides was the length of BC, that square would be greater, it would have more area than the square on A. Okay? How much greater? I say the square on BC is greater than the square on A by the square on a straight line commensurable with BC. So, we're going to find a straight line. It's going to be commensurable with BC. Okay? So we're going to have a straight line, and that straight line will be able to be measured by some number that can also measure BC. And if we take that straight line and make it into a full-blown square, then that full-blown square will be, what you'll do is you'll take the square of A, you'll add it to that other square that we were talking about, and that area, those two areas combined, will be the same amount as the square on BC. That's what he's trying to say. For let BC be bisected at point E. Now, when we're talking about bisecting here, we got BC here. See, there's BC right there. And when you bisect it, that means that BE is going to be the same length as EC. That's what they're talking about. Okay. And let EF be made equal to DE. Okay. So now we're going to draw another line F. And we're going to say that EF and ED are exactly the same length. That's what we're going to say. Okay. Therefore, the remainder DC is equal to BF. Okay. So now we're going to say that CD is exactly the same length as BF. This one here is the same length as this one. That's what we're going to say. And since the straight line BC has been cut into equal parts at E and into unequal parts at D, therefore the rectangle contained by BDDC. Can you draw that out? I bet you can. Go ahead and do it. You have a rectangle. Two sides of the rectangle are going to be the length of BD. Two sides of that rectangle are going to be the length of DC. Therefore, the rectangle contained by BDDC together with the square on ED. Now, what does that mean? That means we're going to make a square, and all 4 sides of that square are going to be exactly the same length as ED. Go ahead, draw it out. Okay, so now we have a rectangle, and the length of 2 sides of that rectangle are going to be BD. The length of 2 sides of that rectangle are going to be DC. And now we have a square, and all 4 sides of that square are going to be the length of ED. And if you add those 2 areas together, you're going to get the area of EC. Okay? Now that means that you're going to draw another square. Okay, we've already drawn a rectangle, we've already drawn a square, now you're going to draw yet another square. And all 4 sides of that square are going to be the length of EC. So, the area of the rectangle and the first square we drew, if you add those 2 together, are going to be the same area as the area of the square you drew with the lines of EC. Exactly the same. Okay? And this is by Euclid Book 2, proposition number 5. And the same rule is true of their quadruples. Therefore, 4 times the rectangle BDDC. Okay, so you have BDDC as a rectangle. Okay, 4 times that area. Okay, together with 4 times the square on DE. Okay, remember we drew that rectangle DE, or that square DE. We didn't draw a rectangle, we drew a square. We drew a square of DE. That area combined with that. Okay, so you take the rectangles area, you add the squares area, you multiply that by 4, and what area are you going to get? Well, you're going to get the area which is 4 times the square on EC. So first of all, you have EC, you've made it into a square, you multiply that area times 4, and you'll get that other area that I was talking about. And if you're confused at this point, let me unconfuse you. All right. Okay, here's that rectangle. Two sides are going to be the length of BD, this side here and this side here. Two sides are going to be the length of DC, this side here and this side here. See that area right there? We're going to add that to this area right here. Now what is this? All 4 sides of this figure are going to be the length of DE. That's right, they're going to be, this is DE, this is DE, this is DE, and this is DE. So if we add this area here plus this area here, we get this area right here. Because the length of every one of these sides is EC. This one here, this one here, this one here, and this one here. Now, if we multiply this times 4 and we multiply this times 4 and we add them together, we're going to get this multiplied by 4. Don't tell me you're confused now, because I know dangin' well you're not. Let's go on. But the square on A is equal to 4 times the rectangle on BD and DC. Okay? So, let's say whoops. Let's just erase that. Let's say that all 4 sides of this are A. This is the length of A, so is this, so is this, so is this. This square is going to be 4 times, okay, it's going to, sorry. This area is going to be the same amount as 4 times the area of this. Okay? Let's go on here. And the square on DF is equal to 4 times the square on DE. Okay. Now we have to draw another square. Okay, and it says, and the square on DF is equal to 4 times the square on DE, for DF is double of DE. Okay? Alright, so what they're saying here is that this is DF. This length here, this length here, this length here, and this length here. That area is 4 times the size of the area in here. And that's because DF, the line DF, which is right here, is twice as long as the line of DE. Got that now? Okay. And the square on BC is equal to 4 times the square on EC, for again, BC is double that as E. Okay. Alrighty, now let's draw this again. Like I said, this gets a little complicated. But I think you're getting this. Okay. So now what we're saying here is the area in this square is 4 times the size of the area in this square. And that's because this line here, BC, is twice as large as EC. That's why we can say that. Okay. Therefore, the squares on A and DF, okay, so now we have A here, we have DF here. If we add these two areas together, guess what we're going to get? The areas of the squares of A and DF are equal to the square on BC. So if we add the area of A and we add the area of DF, we get the area of BC. Add this and this, we get the area of the square of BC. You can visualize that for yourself. So that the square on BC is greater than the square on A by the square of DF. Okay? It is to be proved that BC is also commensurable with DF. So now we have to prove that BC, this whole length here, and DF, this length right here, okay, BC first, then DF next, both of those lines can be measured by another number. That's what makes them commensurable. Since BD is commensurable in length with DC, okay, since BD, right here, this length right here, is commensurable with DC, okay, BD and DC, their measurements are commensurable. Therefore, BC is also commensurable in length with CD. So, the whole BC is commensurable in length with the whole CD. And this is by Euclid Book 10, proposition number 15, which we just covered a few proofs ago. But CD is commensurable in length with CD. Okay? Well, that's obvious. Let me say that again. But CD is commensurable in length with CD and BF. So, what they're now saying is, or what he's saying is, so the length of CD here is commensurable with the length of CD plus BF. Okay? So if you add the length of CD and BF together, that whole sum is commensurable with CD, and that is because CD is the same length as BF. And that's by Euclid Book 10, proposition number 6. Therefore, BC is also commensurable in length with BF. The whole BC is commensurable in length with BF and CD. So, this sum here is commensurable in length with BC. And this is by Euclid Book 10, proposition number 12. Okay? So that BC is also commensurable in length with the remainder FD. Okay? So BC is commensurable with FD. Okay? And this is by Euclid Book 10, proposition number 15. Therefore, the square on BC is greater than the square on A by the square on a straight line commensurable with BC. That is what we were trying to prove. But there's more to this proof. Okay? Let's just go through the rest of this very quickly because you now know what I'm talking about here. Next, let the square on BC be greater than the square on A by the square on a straight line commensurable with BC, which is something we just proved a minute ago. Let a parallelogram be applied to BC equal to the fourth part of the square on A, which is something we just talked about a little earlier in this proof. And deficient by a square figure, let it be the rectangle BDDC. We've already talked about that earlier in the proof. It is to be proved that BD is commensurable in length with DC. So now we're trying to prove that BD is commensurable in length with DC. With the same construction, we can prove similarly that the square on BC is greater than the square on A by the square on FD. Okay? So the area of the square BC is going to be larger than the area of the square on A by the area of the square on FD. And you know how to do this because I just showed you that earlier in this proof. But the square on BC is greater than the square on A by the square on a straight line commensurable with BC, which we just talked about a little while ago. Therefore, BC is commensurable with length FD, so that BC is also commensurable in length with the remainder, the sum of BF and DC. And that's by Euclid Book 10, proposition number 15. So, if we add BF and DC together, okay, we add these two together, it's going to be commensurable with BC, the whole length of BC. Okay? But the sum of BF and DC is commensurable with DC. This is by Euclid Book 10, proposition number 6. So that BC is also commensurable in length with CD. So, the whole length BC is commensurable with CD. That's what they're saying. And this is by Euclid Book 10, proposition number 12. And therefore, separando, BD is commensurable in length with DC. So now we can say that BD and DC are commensurable in length. And that is by Euclid Book 10, proposition number 15. So if you use everything I've taught you at the beginning of the proof, for the later parts of the proof, you'll begin to see what I was talking about. That's why I started slow and then I moved a little bit faster. Alright, that's the end of that proof. I will tell you more in a future video. Stay tuned.